welcome to class. This is week 11 out of I think 18 weeks total. So you guys are more than halfway through. Welcome back from spring break. We're gonna start today. I'm gonna share my screen and keep yourself unmuted. I want to hear from you guys. I'm gonna share my PowerPoint real quick of today's announcements. All right, can you guys see that?
Yeah.
All right. Okay, so today our Zoom session is between 1 to 3:30 p.m. Remember that we have one on Wednesday, and that's going to be at 10 a.m. So I kind of switched the times for just for several reasons, but I switched the times. And sorry if there was any confusion for some of you guys that thought it was going to be at 10 a.m. today. So first thing, since there's just a small class group of us today, I just want to check in. How was your spring break? So I'll leave the floor open. I'd love to hear from you guys. Garrett, why don't we start with you?
Didn't really do much. I've been working on projects.
You've been working on some projects, is that what you said?
Yeah, I have projects, and I have my own test coming up soon.
Wow, okay. How about I'll go through this right here. How about Anthony? How was your spring break?
I just caught up on anatomy or like worked ahead on my book.
Cool. So you're taking another class, anatomy?
Yeah, anatomy and history.
Okay. Good for you for doing your work during spring break.
Yeah.
Victor, how was your spring break?
My spring break was good. I just finished a project that was due today, during spring break for our class.
Oh man, you had homework during spring break?
Well, it was due the day before spring break,
Mm-hmm.
but he pushed it back because, I mean, why not? It gives us more time.
Okay, cool. Did you feel good about the end product?
Yeah, I'm pretty sure it's good.
Cool. What was your project about, if you don't mind me asking?
We had to take it was a colored project, so what we do is we do foliage, I think it's called, and that's
You sent me your student spotlight, so I'll have you share today. Was there anyone else that wanted to do their student spotlight today?
Can I do mine because the last time we didn't have time for it?
Yes, is that Margot?
Yeah,
Okay, so Stephanie and Margot. Margot, are you 130 or 140?
I'm 130.
Not 130. Okay, alrighty. Sounds good. Was there anyone else that wanted to go today besides Stephanie and Margot? Alrighty. And Margot, have you sent it to me already?
Yeah, you should have it.
Where did you send it?
I sent it on your email.
Email, okay. All right, I'll look that up later.
Okay.
Sounds good. All right, so a couple of things in terms of homework. We're going to finish radicals today. This is part B, and that's going to be due on Thursday of this week. We're going to have an online quiz also on Thursday. It'll be available all day, so you guys can take it anytime on Thursday. Continue sending me your student spotlights, reminding you also of the Math Success Center. They're available for online tutoring as well as doing your online DLAs and SLAs. Again, these things I already indicated earlier. We're going to have Confer Zoom this Wednesday at 10 a.m., not 10 a.m., 10:10. Group 5, you guys will be presenting on Wednesday. Next week will be Group 6, so start getting ready. Reminder that Garrett's tutoring is still available on Discord. Did you want to say anything, Garrett, about this?
No.
Nope. Okay.
I'm there.
All right.
No.
All right, and the YouTube videos are still up. I'm going to be uploading more videos today, so you guys on the coming topics. All right, so this is what we did last 2 weeks ago, and this was due on Sunday, and this is what we're going to be dealing with today. Okay.
Wow. Hi everyone, this is Professor Nancy Mahan. Today we're going to go over Radicals Part B. But before we go over Radicals Part B, I just wanted to review what Part A was about before we enter into the new topic. So in my previous Zoom session and video, we went over radicals part A. And the topics we went over is, what is a radical? We talked about its relationship with exponents and how do you simplify a radical. So as we talked about what is a radical, we talked about how do you simplify a radical, and there were two specific methods that I taught you guys. The first one was to rewrite the radical as a product of a perfect square if it's not already in terms of a perfect square. And the other method was doing it as a factor tree trunk. The other thing that we learned about simplifying radicals is the relationship between radicals and exponents. That if you have a radical in this form, this is the index and this is the radicand. So those are the definitions and terms we talked about. You could rewrite it as an exponent where a to the n stays the same, and then the index m goes downstairs in the fraction of the exponent. We also learned about how do you add and subtract radicals, and it was very similar to what we've done before with combining like animals. So you could go back to that and see that when you add or subtract radicals, you have to have like radicals in order to combine them. And what it means to have a like radical is that the radicand is the same and you add the coefficients. And then the last thing we learned from radicals part A is how to multiply radicals. And that was a little bit more simpler because basically what you do is you take the radicand, the B and the D, and you multiply them together, and you take the coefficients in front of them, A and C, and you multiply those together. So whatever's inside the radical, you multiply together. Whatever's outside the radical, you multiply together. And you always want to simplify your radicals and simplify the radicals before you get your final answer. So before we go into part B, make sure that you understand how to do part A. And if you have any questions on part A, go back to those videos to learn that material before we go to part B. So today we will be learning about radicals part B, and those last three topics, or those last three categories, has 20 topics on your Alex homework. And those three main categories is one, how to rationalize a radical. So so far we've learned how to add, subtract, and multiply radicals. So you might be wondering, how about dividing radicals? Well, dividing radicals, what we call it is rationalizing a radical. So we'll talk more about that. Then we always end up every section on how do you solve an equation. So how do you solve equations that have radicals in it? And then lastly, we'll talk about the complex imaginary number system. So this is really cool because so far we've been talking about real numbers, but now we're going to be talking about imaginary numbers. So here we're going to start off with how to rationalize radicals. Well, before we start, let's talk about the word rationalize. The word rationalize means to get rid of. So we're going to get rid of the radical whenever we have an expression. So if we look at topics number 1 to 7 in your worksheet. So here in your worksheet, numbers 1 to 7, you have all these radicals in terms of fractions. And when we talk about fractions, we think of it as division, right? Because fractions are like division. So again, we've learned how to add, subtract, and multiply fractions, but how do you divide fractions? Well, we're not going to divide the fractions. We're going to rationalize the denominator of these fractions. So notice the words rationalize the denominator. So in other words, we want to get rid of the radical in the denominator of a fraction. Notice that all of these instructions or directions says rationalize the denominator. If it says rationalize the numerator, then of course you're going to want to get rid of the radical in the numerator. But in this class for algebra, we're only rationalizing the denominator. But in calculus and maybe other topics, you might be asked to rationalize the numerator. So the question is, how do you get rid of this? How do we get rid of radicals in a fraction? So the first thing we want to, before we get into that, the first thing I want to note is a reminder of a few things. If I had square root of 3 times square root of 3, we're going to get square root of 9, right? 3 times 3 is 9. Well, 9, the square root of 9 is simply just 3. Let's look at another one. If I get square root of 4 times square root of 4, I get the square root of 16. And what's the square root of 16? 4. Notice the pattern here. Square root of 3 times square root of 3 just gives you 3. Square root of 4 times square root of 4 just gives you 4. So if I ask you what's the square root of 89 times the square root of 89, instead of multiplying these two to get some big number and then simplifying, notice that the shortcut is that when you multiply a radical by itself, in this case, then you end up just getting the radicand, the number inside the radical. So square root of 3 times square root of 3 is just 3. Square root of 4 times square root of 4 is just 4. Square root of 89 times square root of 89 is just 89. Same thing with if you have letters. If I have square root of x times square root of x, the answer is just x, right? And this is because of what a radical is. What a radical is asking us, what number do you multiply twice to give you the number 9? Well, the things that you're multiplying twice is the radicand inside. So square root of 3 square root of 3 is equal to 3. So just a reminder of that. So another way of writing this then is if I'm doing square root of x times square root of x is equal to x, I could write this as square root of x. If I squared this, that'll just give me x, right? If I put the square root of 27 and I squared it, I just get 27. So this is another way of writing this here. Multiplying by itself, or you can say you square it. So this is the big kahuna idea of how do we get rid of radicals in a fraction. So let's take a look at number 1. So example number 1, I have the square root of 13 over the square root of 52. So square root of 13 over square root of 52. So I noticed that the direction, basically what I want to do is I want to get rid of the radical in the denominator. So if I want to get rid of the radical in the denominator, I am going to multiply. I want to get rid of this radical. How do I get rid of square root with a 52 in it? I basically want this to equal just 52. So I don't want the radical in there. Well, knowing what we know here, what do we need to multiply by to get 52 sitting by itself without a radical? We multiply it by itself. So square root of 52, if I multiply it by square root of 52, similar to what I just did here, then the answer is just 52 without the radical. That's pretty cool because now I have no more radicals in the denominator, and that's called rationalizing the denominator. And what we know with fraction and with mathematics in general is whatever you do once on the bottom, you must do the top. So it must be balanced, right? So since I multiplied by square root of 52 on bottom, I also must multiply by square root of 52 on top. Now, what is square root of 13 times square root of 52? Well, I don't have a calculator on hand, so I'm just going to do this the old-fashioned way. I get 676. That's a really big number. So 600, let me check my answer. 6, 2, 15, 6, 6, 7, 6. That's right. So here I get this huge fraction. And what we know with big fractions like this is that we always want to make sure that we simplify it. All right, and before I keep going on, let me ask you, what did I just do wrong here? I put 52, the root, but multiply together I get 52. 13 times 52 plus 676. What am I missing? Oh, that's right. I'm missing the square root. So make sure when you're multiplying radicals, you have that radical over that. So even though the radical in the denominator disappeared because of this here, the top 13 times 52, remember there's always a square root on top. So square root of 676, if you actually just plug that into your calculator, 676, you take the square root of that, you end up getting 26 over 52. And 26 over 52, remember we always want to simplify our fractions whenever we answer it. They're both divisible by 26, so we end up getting 1 divided by 2, or 1/2. So the answer for number 1 is 1/2. Now let's take a look at something. Let's make it a little bit more complicated. Let's look at example 2. So example 2 here, I have 5 over the square root of 3. Again, the direction is to rationalize the denominator. So I want to get rid of the radical in the denominator. So to do that, I'm going to multiply it by itself, right? So if you multiply square root of 3 by itself, you end up getting square root of 3 times square root of 3 is just 3, as we did up here, right? Square root of 3 times square root of 3 is actually square root of 9, but if you simplify, that's just 3. But you could just shortcut it by saying if you multiply a radical by itself, you just end up getting the radicand, the 3. So here's that, and remember, whatever you do bottom, you do to the top. So 5 times square root of 3 is not square root of 15. So be careful, this is not square root of 15. I see students do that a lot. Remember that when we're dealing with multiplying radicals, the numbers on the outside of the radical stays outside, and the numbers inside the radical stays inside. So here we have 5 root 3 over 3. And you might be wondering, well, there's a root 3 here. Do I need to get rid of the radical? And the answer is no. It's okay to have a radical in the numerator where it just asks to rationalize the denominator. So therefore, this becomes the final answer for example 2. All right, now let's take a look at example 3. So again, each one's going to get a tiny bit harder. So here in example 3, I'm going to have the square root of 7 over 5. So when you look at this, you might be saying, well, I don't see a radical in the denominator. Well, actually, there is a radical in the denominator because this radical is over the whole fraction. This can be rewritten as radical 7 over radical 5. So this is one of the rules of radicals. So I'll write it as on the side here that notes if you have a fraction under a big radical, the radical is applied to both the numerator and the denominator. So just be aware of that. So therefore, when you have a fraction under a radical, you can break up the radical from the top and the bottom. And now that you have it in this form, we're going to do what we did earlier, where I want to rationalize the denominator. So to get rid of the square root of 5, I'm going to multiply it by itself. And again, when I multiply it by itself, root 5 times root 5 just gives me 5. Similarly, whatever you do on bottom, you do on top. So on top here, square root of 7 times square root of 5, well, because they're both underneath a radical, I can multiply these together, and I get square root of 35. Right? And can I simplify square root of 35? The answer is no, because the only thing you could simplify 35, if you break it down to 7 times 5 is 35. Square root of 7 times square root of 5 cannot be simplified anymore, so that is what it is. And that becomes your final answer for example 3. Now let's go ahead and throw in some variables or some letters in this problem. So example 4 here, I'm going to have square root of 5 over square root of 3z. So square root of 5 over square root of 3z. So to do this problem, just because it's a variable, don't be scared. It's the same idea. So I'm going to multiply the denominator by square root of 3z. So when I do that, this times that will just give me the radicand. Again, the radicand is just what's inside 3z. When you multiply a radical by itself, you just get the inside. And again, whatever you do bottom, you do to the top. All right, so when I do that, this times that, since they're both underneath the radical, I can multiply them together. So here I get square root of 15z all underneath the radical. And you might be tempted to, oh, can I cancel anything out? And the answer is no, because square root of 15 and 3 this is underneath a radical and this is not underneath a radical. You can't cancel them out. It's not saying 15 divided by 3 and I could cancel things out. Remember, it's square root of 15 and divided by the 3. So therefore, nothing can be canceled out. So please don't cancel things out. And this becomes your final answer for example 4. All right. So now we're going to make it a little bit harder. What happens then if the denominator looks a little bit more complicated? So notice in these problems here, the denominator is a monomial, meaning there's only one term in the denominator. Monomial, there's only one term. But what happens when you look at questions 5 through 7? Notice the denominator has two terms. So these are what we call dividing by binomials. So how do you rationalize the denominator when it's a binomial? So let's talk about that. So rationalizing the denominator when it's a binomial. So again, a binomial means that there's two terms. So there's two terms in the denominator. So let's look at number 5. So example number 5, I have 5 over 3 square root of 5 minus 2. So if you kind of try to apply the same logic of what you did up here, multiplying by itself, I just want to show you why it does not work. So if I multiplied this by itself, 3 square root of 5 minus 2, what if I multiplied it by itself? 3 square root of 5 minus 2, what's going to happen? So if I multiply it by itself, if I FOIL it per se, I'm going to get, so here, if I multiply it by itself, 3 times 3 is 9. Square root of 5 times square root of 5 is just 5. So 9 times 5. So that becomes 45. So 3 root 5 times 3 root 5 is 45. 3 root 5 minus 2. So first outer now. First, then outer, then inner, then last, right? So here, I multiply the things outside the radicals together. So 3 times a negative 2 is going to give me a negative 6 inside the radicals of 5. Then I multiply the inner. So here, negative 2 times 3 is negative 6. Inside is 5. And then negative 2 times negative 2 is positive 4. So notice when I multiply it by itself, negative 6 root 5, negative 6 root 5, I can combine this. I get 40, and 45 plus 4 here will give me 49. And then here I have minus 12 root 5. Uh-oh. Right? We still have a radical in the denominator. So multiplying the denominator by itself when it's a binomial doesn't fix the problem, right? You still have a radical in the denominator. So what do? So what we do is this. It's called multiply. Instead, let me write this here. So I'm going to say instead, so here I put multiply by itself, and the answer is no, right? So instead, we multiply the denominator by what we call the conjugate. The conjugate of the denominator. So the conjugate of the denominator, what is a conjugate? So the conjugate, if I gave you 7 plus 2, the conjugate of 7 plus 2 is 7 minus 2. If I gave you x plus 20, the conjugate of x plus 20 is x minus 20. If I gave you 10 minus y, the conjugate of 10 minus y is 10 plus y. Let me give you another one, and hopefully you see the pattern. If I gave you negative w minus 4, the conjugate of negative w minus 4 is negative w plus 4. So what do you see here? So I hope you see that the conjugate is really just changing the middle sign. So conjugate changes the middle operation from adding to subtracting or vice versa. So the first number stays the same. So 7, here's 7. So the sign stays the same. But when I have plus 2, I change it to minus 2. Plus 20, negative 20. Minus y, plus y. Negative 4, plus 4. So conjugate changes the middle operation from adding to subtraction or vice versa. So in this case, in this problem here, I have 3 root 5 minus 2. So let's write this down as a new problem then. So 5 over 3 root 5 minus 2. If I'm asking you to multiply by the conjugate of the denominator, what's the conjugate of this? So the conjugate of this, hopefully you'll see, is 3 root 5 plus 2. So all you do is you multiply it by the opposite sign there. So you might be wondering, well, why am I multiplying by the conjugate? Is that going to get rid of the radical? Well, let's see. Well, we know that when we multiplied it by itself, it did not get rid of the radical, right? But if we multiply it by the conjugate, what happens? So here, I'm going to put parentheses around here. So I'm going to multiply these two, and that's why it's important that we know how to multiply radicals at this point. So 3 root 5 times 3 root 5 is 9 times root 5 times 5 is 5. So again, that becomes 45. 9 times 5 is 45. 3 root 5 plus 2 is plus 6 root 5 because we multiply the things outside the radical together. Then right here, 3 times negative 2 is negative 6 root 5. And then here, negative 2 times 2 becomes plus 4. So here, notice what happens. So the 45 and the 4 adds up to give me 49. And what happens to the middle terms? They cancel out, right? So 6 root 5 and minus 6 root 5 cancels out just to become 0. So therefore, you end up just getting 49 in the denominator. So voila, as you can see, when you multiply by the conjugate, the middle terms always cancels out, or it zeroes out, right? Because one's a positive, one's a negative, and you're only left with the first and the last term, and the first and the last term do not have radicals in it, so you end up getting 49. And this is going to be true for all problems. So in general, note this. If you have A plus B times A minus B, so notice if you're multiplying two polynomials where one of them is the conjugate of the other, so notice this is the conjugate of that, or this is the conjugate of that. If they're conjugates of one another, if you multiply them together, notice, so if I did FOIL, I get A squared, A times negative B is negative AB, B times A is plus AB, or BA, doesn't matter the order, and B times negative B is negative B squared. Notice the middle terms, negative AB and positive AB, always cancels out as it did up here, and you're always left with A squared minus B squared. So here, this is the shortcut. This is the shortcut of multiplying conjugates. A plus B times A minus B is equal to A squared minus B squared. And I also want to point out something super duper cool. Do you notice that this is the formula of difference of two squares? The difference of two squares, the dots when we factor it. So super cool how things come together. A squared minus B squared is the difference of two squares. And if you factor the difference of two squares, you get A plus B, A minus B. And that's what factoring is, right? You're just going in reverse order from distribution. So this is also the difference of two squares. So very cool shortcut to do. All right, so back to this problem. I have the denominators rationalized. The numerator, whatever you do bottom, you must do to the top. So when I do that to the top, I multiply 5 times everything here. So 5 times this, remember the things outside the radical, you multiply together, so you get 15. root 5 plus 5 times 2 is 10. Right? So here I ask myself, well, can I simplify or can I factor anything out? And when I look at the top, 15 root 5 and 10, what do they both have in common that I could put? What's a GCF? Well, the number 15 and the number 10, they both have a GCF of 5. So if I pull out a 5 and I factor that out, again, factoring comes into play again. 5 times what will give me 15? 3. And then I need a root 5. Plus 5 times what will give me a 10? 2. So here I have factor, factor, factor. And I ask myself, are there any common factors that I can cancel out and simplify? And the answer is no. 5 and 49 have no common factors. 3 root 5 plus 2 and 49 have no common factors. So therefore, you could leave your answer as this because it can't be simplified anymore. Or you could always write your answer as this. They're both acceptable. Either one. So let's rewind this problem real quick. What did I do wrong in this problem? So hopefully you guys caught it. Notice right here, when I was foiling it, I got 45 plus 6 root 5 minus 6 root 5, but a negative 2 plus a 2. What's a negative 2 plus a 2? I mean, what's a negative 2 times a positive 2? You should get a negative 4 instead of a positive 4. So this is where I went wrong. I should have said minus 4. Hopefully you guys caught that while I was doing it. 45 minus 4 then should be 41. And I caught this because, oh, and let me just change this to a 41, and I'll change this to a 41 as well. Okay. And I caught this because as I saw that when I was looking at the shortcut of foiling, it should be, when you multiply by conjugate, you should get a squared minus b squared. So you take the first term, 3 root 5, and you square it. So when you square that, you get 45. And then minus the second term when you square it. So here, when I square the second term, I should get a 4, right? So 2 times 2 is 4, but it should be a minus 4. So I put a positive 4 initially, it should have been a minus 4. That's how I kind of caught myself with that error. So as you can see, math teachers make mistakes as well. We're human, just like you guys. However, that's why it's really important to double check our steps. All right, so for our next problem here, it looks a little bit messier, but it's still basically the same idea. So I have a binomial in the denominator. So what I need to do is multiply by the conjugate. So what's the conjugate of the denominator? So hopefully you wrote root 11 plus root 3. So you multiply it by itself, but you change the sign in the middle. And remember, whatever you do on bottom, you also must do on the top. Because it's a fraction, and that's in mathematics, it's all about keeping things fair. So I'm going to put these in parentheses to emphasize that I'm multiplying these polynomials together. So when I do the denominator, this times that, I'm multiplying by the conjugate, so I could FOIL it, but you know what? Now that we understand what happens when you multiply conjugate, I'm going to do the shortcut. So the shortcut is when you FOIL it, the two middle terms always cancels out. So here, when you FOIL something, the two middle terms always cancels out. So the shortcut is that you just take the first term and you square it, a squared, minus, you take the second term and you square it. So instead of FOILing it, because the two middle terms are going to cancel out anyways, I'm going to do the shortcut. So root 11, I'm going to square that. So let's just think of this squared. So square root of 11 times square root of 11, that's going to give me 11, right? Because I square it. And then I look at the last term, so I have minus root 3 times root 3. So root 3 times root 3 would just give me 3. So in the end, I end up just getting 8. So that was so much faster than FOILing it because, again, if I FOILed it, I would get a positive of this and then a negative of this, which would cancel out. So why do all that when it's going to cancel out anyways, when it's going to zero out? So here, as a result, the denominator becomes an 8. Voila! No more radicals. The top, however, we can't do any shortcuts, right? We're just going to have to multiply these two out. There's no shortcuts. There's no conjugates here. So you just have to multiply it out. So again, reviewing how do you multiply radicals, if you guys recalled what I did in my previous lecture, to multiply this radical here, so I'm just going to write it out on the bottom. To multiply this out, you could FOIL it, or if you want, I prefer organizing my multiplications by creating a table. The first polynomial I write up here, and then the second polynomial I write down here. So the second polynomial, I write them as rows. The first polynomial, I write them as columns. So now all I have to do in order to multiply is I just cross multiply from the rows and columns. So here, 3 root 11 times root 11, that's going to give me 3. Root 11 times root 11 is going to give me 11, right? Because 11 times 11 in terms of its roots will just give me 11. So 3 times 11, that just gives me 33. This times that, they're both under the radical. I multiply them together, I get square root of 33. This times that, well, outside the radical is 3. Inside the radical is 11 times 3. Inside the radical is square root of 33. And last but not least, root 3 times root 3 will just give me root 9, but root 9 is just 3. So root times itself is just the radicand. So now, remember with multiplication, after you cross multiply, or after you multiply rows and columns, then you add all of these up. So when you add them all up, you ask yourself, are there any common radicals that you can combine, or any common terms? So I'm just going to write it out here so it's really clear. So if I add all these up together, the ones that combine is 33 and 3. That'll give me 36. These are like radicals, right? Because the radicand is the same, root 33 and 33. There's an invisible 1 here, the coefficient. So if I add these two together, 3 plus 1 is 4. And inside the radical stays the same. So again, this is a review of multiplying radicals and adding radicals. That's why we learned this in a previous lecture already. So this is the numerator. So up here, I get 36 plus 4 root 33. And then I ask myself, can I simplify this? Well, in order to simplify it, I need to factor it, right? So you can't just say, oh, 8 and 4, they can cancel out because they have a common number. No, they need to be factors in order to cancel out. So when I look in the top, this is my first term, and this is my second term. And I ask myself, do these two terms have a greatest common factor? Well, outside the radical is the 4 and the 36. So yes, they have a greatest common factor of 4. So I'm going to pull out the 4. Inside the radical, well, factoring 4 times what will give me 36? 9. 4 times what will give me the second term? Well, 4 times a root 33 will give me the second term. So I double check that by distributing. I get 4 times 9 is 36. 4 times root 33 will give me that. So I factored it. The bottom, I have 8. So this is a factor, factor, and factor. So now I can cancel out or divide out common factors. So what are the common factors? Well, 4 and 8 have a common factor of 4. So I could divide out a 4 in these two common factors, or these two numbers. So 4 divided by 4 will give me 1. 8 divided by 4 will give me 2. So therefore, my final answer, the simplified version, well, 1 times all this, I don't have to write the 1. So I just put 9 plus root 33, because the multiplying by 1 doesn't change anything, divided by 2. So this here becomes the final answer for this problem.
-1.
Yes.
Okay. Did anyone get an answer for the denominator? So the denominator should just be something without a radical. Did anyone get anything when you multiplied it by that?
4u minus 1.
Great.
Yes, that's what I got.
4.
That's right.
Great. So 4u minus 1. Can someone show their work? Share a screen and show it on your cell phone or laptop. How you got 4u minus 1?
I didn't show exactly how you did it, but I did what you did, like square root to square root of u. So I multiplied that by the square factor.
Can you share your screen by any chance, Jennifer?
Because I don't have the work. Like, let me show you.
Okay.
I literally just like did it in my mind. Right here.
Okay, so go ahead.
It literally just goes right away to 4u minus 1.
I'm going to spotlight your video. Okay.
So it was just 2 times 2, which is 4. And then since square u is just going to be u. So 4u, because you multiply 4 in the u. And then 1 times -1 is -1.
Great. So can everyone see? Can everyone see her work? 4u minus 1. Any questions? That is correct. And then the top part, can you explain what you did with the top part?
Let me see. So I multiplied -7 times 2, which is -14. And then since there's no square u, to multiply is going to be square u. And then it gave me +7 because -7 times -1 is +7. Equals 7, sorry. And then I don't know if the answer is right, but I got when I simplified it, if I can, I got -7 parentheses 2 square root u minus 1. And then in the bottom, I got 4u minus 1, sorry.
Right. So we can't cancel anything out, right? We can't simplify anything out?
No.
Right. So yeah, that's actually absolutely correct. So what Jennifer did, the final answer is -14 square root of u plus 7 all over 4u minus 1, what she wrote up there. And then she simplified it by trying to factor out a GCF of 7 in the numerator. But when she factored it out, she couldn't simplify. Nothing could be canceled out anyways. So therefore, she could just leave her answer in the first way, the -14 u plus 7 all over. Does anyone have any questions with what Jennifer did? Any questions at all? All right, excellent work, Jennifer. I know a lot of you guys mentioned that was a really hard problem. Anyone have any parts that were fuzzy, or was that pretty clear?
So when you multiply a square root and there's no square root, like for example, the u and 7, how we have to move it on top, you don't plug it into the square root.
Jennifer, can you show your work again?
Yeah.
Okay, so what was your question again, Abraham?
I think he was talking about if there was no more square root to multiply this. Right.
Because -7, and you know how
Right
you're
here,
yeah.
Because there's no square root. Yeah, you would just leave it over here the same because you're not multiplied by any square root.
So.
Right. Good. Yeah. If there's no square root, then that means it's outside the square root.
All right. Thank you.
Good. Good question. Any other questions? All right, perfect. At this time, it's 2:24. I'm going to give you guys a shorter, a little bit of a shorter break until 2:30. So 6-minute break. Go ahead and go to the restroom, do whatever you want. Take a break, and I will see you guys at 2:30. All right, welcome back, everyone. And Stephanie, your student spotlight. Go ahead.
Okay. On the first picture to the left, it's when I used to go to Disneyland, when I used to have the pass, and I used to go like almost every week. But then with this happening, I can't go no more until I think May 15. As of now, on the middle picture, in the top, it's my favorite food, which is seafood. I love seafood. And then on the third one, my favorite show is Stranger Things. This picture was from Universal Studios Horror Nights, which was, I think, 2018. It was 2 years ago. And then on the bottom one, I am Mexican. It was last summer where I went to Guadalajara, where my mom's from. And I do have a Frenchie dog. His name is Rico. And I love going to the beach, lakes. I love going out like with my family and friends. And then that's pretty much it.
Cool. Anyone have any questions for Stephanie?
Your favorite ride at Disneyland?
It's the Cars one.
What do you miss most during the quarantine time?
I like going out, like on the weekends, to the mall, to the park, to the beach.
Mm. I think, can you still go to the beach where you're at? Are you in Long Beach?
Yeah.
Okay, I guess, yeah, I know Long Beach is LA County. You can't go to the beaches anymore, right?
No, everything's closed down right now.
Right. I think there are some Orange County beaches that are open that you could still walk around and do things.
I'm not sure if it's the one on by the Pike. I don't know if that one's open.
Oh, by the Pike? I'm not sure.
Uh-huh.
I know Corona Del Mar and Huntington Beach, like the pier is open and you can still walk on the beach and stuff.
Oh, okay.
Cool. Is your mom in Guadalajara right now, or that's just where she was from?
No, that's where she was from.
Okay. Awesome. Any other questions for Stephanie? All right. Thank you, Stephanie, for sharing.
You're welcome.
All right. So next up, we have Margot. So Margot, I think you just sent it as pictures, right?
I did because my PowerPoint isn't working.
No worries. Okay. So let's go. I'll go ahead and just go through photo by photo then, and then.
Okay, that's fine.
Yeah. So this is Margot. Go ahead.
Okay, so this picture right here, I want to be a makeup artist. So this is my last year at Long Beach City College. So I'm hoping to be a makeup artist for celebrities, for like TV shows and movies. And then you can go on the next one. This photo right here is soccer. So I am a soccer player. I started soccer when I was like 6 or 5 years old, and I love it. Unfortunately, I can't play right now because of the quarantine, but soccer is my number one favorite sport. Then you can go. So I am actually 100% Greek. I've actually traveled to Greece. It's been a while since I've been to Greece. It's been like 10 years. I was hoping to go to Greece this summer, but I can't, so.
Oh, sorry. Well, hopefully, maybe, who knows?
Right? You can go to the next picture. So I am a coffee drinker. I love coffee. I can drink up to like 5 or 6 cups of coffee a day if I can. I'm a coffee addict. I don't know what to tell you guys. Go to the next photo.
Well, at least you can still drink coffee during these times.
Yeah. So then I love makeup. So my favorite makeup brand is ColourPop. And I feel like I have like 10 or 20 eyeshadow palettes in my bathroom.
Wow.
You can go to the next slide. And then that's a picture of Greece that I told you I traveled to, that I want to go back. And then you can go to the next picture. And then I love going to the beach with like my friends. I think like the beach is so much fun, going in the water and just going on the sand, just getting a tan. And yeah, I think there's one more. And then New York is my favorite place. I want to move to New York and live there and hopefully start a family out there.
Wow. Why New York?
I just like the high speed of everything. You know, you walk places, like your apartment can be right here and then the grocery store is like two doors down. You don't have to drive anywhere. I think I just like how like everything is laid out there.
Have you been there before?
I have. I've been there like 10 or 12 times. We try to go every summer for like a week, and we go to like plays, and we go to like Central Park, and we'll go out to dinner. My family and I really enjoy going to New York. It's a lot of fun.
Cool. All right, any questions?
Oh, there's one.
Yeah.
And then I'm a fashion merchandising major. That's basically it.
Cool. Any questions for Margot?
So do you watch soccer?
I do watch soccer. I haven't been watching it lately, but I'm more like into going into the game, like watching in the stands more on television because I will scream and my mom will get mad at me because I'm a perfectionist on when it comes to soccer.
Do you have a favorite team?
Do I have a favorite team? I do like watching the World Cup, the girls. I don't have like a team soccer team that I like. I just watch the World Cup whenever it comes on.
Great. Any other comments or questions for Margot?
I better command you. No, I'm just kidding.
What did you say?
That's a soccer thing.
Oh. Any other comments or questions? Okay, super ignorant question, but I've never been to Greece. It's made up of a couple of islands, right? Or is it one island?
No, yeah, there's different islands. So there's Athens, Santorini, like you can go island hopping. Each island is very different.
Wow, I would love to go there one day.
What's your favorite island?
I want to say Santorini, but it's been a while. So I was 13 when I went, so I don't really remember a whole lot. But I know that, you know, like the beaches are very different than our beaches. Like you can see like it's very clear, very blue. Like when you go in, you can see like the fishes swimming around you. It's not cold. A lot of like interesting things you can do at in Greece. They like to stay up late too. Like they'll take a nap at like in the middle of the afternoon, and then the whole town will be like totally like a party. Like they don't go to bed until like 6 or 7 o'clock in the morning. Like everyone's like eating dinner, drinking, partying the whole night.
Well, hopefully some of us will be able to go. We'll be able to go one day.
Yeah, definitely.
Yeah, definitely on my bucket list.
Yeah, definitely go.
Awesome. Well, thank you both, Margot and Stephanie, very much. Alrighty, so we are going to continue on now with numbers 1 through 7. Can you guys all see that? I'm not going to do my whiteboard that keeps falling down more. I'm going to try something new doing this. So now from questions number 8 to number 14, we are now into solving equations. So here we're going to solve, make sure you guys can see that. Now we're going to solve equations with radicals. So again, equations are things that have equal signs in them, right? So here from number 8 to number 14, those topics, we're going to talk about solving equations with radicals. So here, let's take a look. So again, this is going to be whenever we solve equations, I like to do it step by step so you guys can see what's going on. And so 1, 2, 3, 4 simple steps. And again, if you miss a step, then off you go flying down, right? So make sure you do it step by step. So the first step that we're going to be doing is that you're going to isolate one radical on one side of the equation. Can you guys hear me okay? Can you guys all hear me?
Yes, I can hear you.
Okay, sounds good. So you're going to isolate one radical on one side of the equation. So if there's 2 radicals, then you just want to make sure that there's only 1 radical on each side of the equation. So let's take a look at number 8 here. So number 8 here, as you can see, already, keeps changing on me. Number 8 here already has 1 radical and it's one side of the equation, so that's A-okay. Number 9 here, this one has a radical, but then it has a -1 here. So remember, we want to isolate. So if we want this to be sitting by itself, what must I do for step 1? Any takers?
Can you repeat that one more time, please?
So if step 1 is to isolate one radical on one side of the equation, what must I do for number 9 to isolate that radical?
You add one?
Yeah, you add 1 to the other side. So in step 1 here, I need to add 1 to that side. So if I add 1 to that side, I'm going to end up with 2 is equal to square root of 3v plus 16. Is everyone okay with that? So I'm just doing step 1 right now. So I'm just going through all these problems doing step 1. Notice this one's a radical sitting by itself, all good in the hood. This one we had to do a little bit of work. Number 10, do I need to do any work to this?
No.
No, right? Because it's the radical sitting by itself. So all good in the hood. Number 11, do I need to do anything with this one? Just step 1.
No.
No.
Yes. No.
It's already sitting by itself. Number 12, it's already sitting by itself. So actually these problems, the radical is sitting by itself. This one doesn't have a radical. We'll talk about that later. But as you can see, there's only a few of them where actually step 1 requires a little bit more work. And it was only that number 9. So again, it's not a big deal. A lot of the problems, the radical is already sitting by itself. But if it's not, just make sure you move it over, right? So that was step 1. Hopefully that wasn't too bad. Now step 2. Step 2 is you want to get rid of the radical. So remember, how do we get rid of a radical? So I'm going to put a reminder here, what we just did earlier. Reminder, if you have something like square root of 4, how do you get rid of the radical sign?
Multiply times the same number?
Yeah, multiply it by itself, right? And another way of saying multiplying it by itself is if you squared it. So if you squared it, you would get, what's square root of 4 squared?
4.
Just 4, right? Or you could think of it as square root of 16, and square root of 16 is 4. So it's just itself. So reminder that even if I have the square root of x squared, if I squared this, I would get x, right? And even if the inside is really ugly and messy, say x minus 9, and if I squared that, whatever is inside here, when you square it, what do you end up getting?
X minus 9?
Right, just x minus 9. So whenever you square something, when you multiply by itself, all it does is it gets rid of the radical and you're left with the radicand. So we did that earlier when we were rationalizing the denominator, but that's the same idea with this here. If we want to get rid of the radical, all we have to do is square it. If you square it by itself, you can get rid of the radical. However, always remember, another reminder of a rule of math is when you have an equation, whatever you do to one side, of the equation, someone complete that sentence. Whatever you do to one side of the equation, you must what?
You must do the same to the other side?
Right. You must do to the other side. Or you must do the same to the other side, right? So the rule of an equation for math is whatever you do one side, you have to do to the other side. So here, if we're going to square one side of the equation, we're going to have to square the other side. So let's take a look then at, number 8. So number 8 here, I have square root of v minus 7 equals 7. So step 1 is already done. The radical is sitting by itself. And what I'm going to do is I'm going to square it. I'm going to square the left side. But remember, whatever you do to the left side, you must do to the right side, right? So if I square the left side, what happens when I square the left side? What do I get?
V minus 7.
Right, v minus 7. And the right side, I get?
49.
49. Great. So now notice you have no more radicals. So then after that, guess what I do? I need to solve for v. So what do I need to do?
Add 7 to both sides.
Great. If I add 7 to both sides, what do I get? V equals to?
42.
I'm sorry?
42.
Not 42. You want to add 7, so?
I mean, sorry.
No worries.
56.
Excellent. 56. And that's the answer. Right? So, and you always want to check your work at the end. So if I plug 56 in here, if I just want to check, my work, I'm going to say, does the square root of 56 minus 7, does that equal to 7? Right? I'm going to check my work here because I plugged 56 into that problem. So 56 minus 7 is 49. What's the square root of 49? 7. Does 7 equal to 7? Yes. So it works. And that's it. That's really all there is. So it's not too bad, right? So the main idea is to get the radical by itself, square it, and then square both sides to get rid of the radical and then solve for it. So let me finish writing out these steps here. So the second step was to get rid of the radical, and how you do it is square both sides. So square both sides of the equation. So that's how you get rid of the radical. So that was step 2.
Will you cover all the topics today, or will you cover some on Wednesday?
We're covering all of them today.
All right, because I have to go, but it'll be online, right?
Yep, it'll be online. Good to have you.
All right, bye.
All right, see you. So get rid of the radical by squaring both sides. And then after you got rid of the radical, then the third thing is just to solve the equation. Solve the equation as usual. So in that problem there, it was a linear equation. So you want to also ask yourself, is it a linear equation or a quadratic? So again, if it's a quadratic, then we're going to have to do factoring and all that jazz. So you want to ask yourself those questions, right? Is it a linear, quadratic, and you solve it as usual? And then the last step is always just to check. Check your work. Check your answer. So those 4 simple steps. Does anyone have any questions on these 4 steps? All right, so let's go ahead and do number 9. So we just finished number 8. Number 9, let me give you guys a chance to work on that. So we already said, we did the first step already. 2 is equal to root 3v plus 16. Let me give you guys a chance to work on that. All right, so help me out. Sophia, are you there?
Yeah, let me flip.
So what did you do? Oh yeah, or you could show your video.
Okay, so is it blurry? I think it's a little blurry.
I think I could see, hold on 1 second. I can kind of see it. Can you just talk it out? Mm-hmm.
So, I added 1 on both sides, and that made the -1 cancel out. So then you get 2 equals radical 3v plus 16.
Okay.
So then I squared both. And then I get 4 equals 3v plus 16.
Okay.
And then I subtract 16 on both sides.
Okay.
And then I got -12 equals 3v. So then you divide both sides by 3.
Mhm.
and then you get v equals -4.
Great. And did you get a chance to check your work, Sophia?
No, I just got to that point.
Okay, great. Do you guys all agree? Did anyone get a chance to check, or do you guys all agree or have questions? Any questions on this?
I think I checked my work and like it didn't work out.
It didn't work out? Okay. So let's take a look at this. If we plug -4 into this problem, 3 times -4 will give me -12, right? What's -12 plus 16?
4.
4. So then it's the square root of 4, right? So if I get the square root of 4, what's the square root of 4?
2.
2. And then what's 2 minus 1?
Oh, I forgot the -1. Never mind.
Right. So good. Well, I'm glad you checked. Yeah, so 2 minus 1 will give you 1. So right, so -4 does check out. All right, great job. Thank you, Sophia, and thank you for sharing what you did. Any other questions? All right, so let's look at number 10 now. Actually, let me see real quick. I just want to make sure we have time for the rest. It's 3 o'clock, so we have half an hour. Let me just skip around because number 10 is going to be very similar. Let's skip around. I'm going to go to, is there any that you guys are dying for me to try doing, or is any okay?
14.
14, all right. All right, actually before I get to 14, let me do another one that's similar to with the radical. Do any of you guys want me to do any of those?
12.
12? All right, let's look at number 12 then. So number 12 here, I have square root of 2x squared minus 4x plus 3 is equal to x. So the radical is sitting by itself, so I don't need to do anything for the first step. The next step then is I'm going to, what do I need to do to get rid of radical? Square both sides, right? So we need to square both sides to get rid of the radical. And after I square both sides, again, it doesn't matter how ugly the thing is inside, you just leave it as is. So you get 2x squared minus 4x plus 3. Because when you square a radical, you just get the radicand. And the right side, you get x squared. Is everyone okay with that? Any questions? All right, so next, what do I do next? Why don't you guys tell me? What do I do?
What do you have to factor?
Right, and why do you have to factor? How do you know we're supposed to factor that?
Because it's a quadratic.
Beautiful, correct. So because it's a quadratic, we need to use factoring to solve it. So here, bubble is, it's a quadratic. We need to factor in order to solve a quadratic, right? Because the highest exponent is 2, we know we need to use factoring. But before I factor, what am I supposed to do first?
Find the GCF.
Not that. Try again. Does anyone know what we do first before we factor?
Move the variable to one side.
Yep, move the variable to one side. In other words, we need to set the equation equal to
0.
0, right? So first thing we need to do is set the equation equal to 0. Set it equal to 0. So that's why we're going to move the x squared to the other side. So I'm going to subtract x squared. So when I do that, what do I end up getting?
Squared.
X squared
Minus 4x
minus 4x
plus 3.
plus 3. Great, thank you. All right, and then now we can factor, right? So make sure you set it equal to 0 first before you factor. Right, so now we can factor. So go ahead and factor that. Anyone know how to factor it? What do we get when we factor it?
-3, -1.
So x minus 3 and x minus 1 when you x pause. Xbox it. Any questions on that? Okay, so again, like, remember when I said that factoring is so important, it comes up in every chapter? Here it is. So after I factor it, what do I do after that? What's ZPP? Did you guys forget?
Zero product property.
Right, the zero product property. So that means that we set each, now that's equal to 0, we set each factor equal to 0 and you solve for it. Right? So what is x equal to?
3.
3. X equals to?
1.
1. Great. So we have 2 answers for this problem. And the thing is, we got to make sure we check it to make sure that it works. So let me give you a chance to go ahead and plug 3 in here to see if it works, and plug 1 in here to see if it works. And just for the sake of time, I'm just going to tell you, yes, it does work, right? So it will work once you put them in. There's times where when you plug it in, one of them will not work. So be careful. Must check. Because there are times where one of them might not work. And if one of them, when you plug it in, doesn't work, then you're going to delete that answer and then circle the other one instead. So always check your work when you're dealing with these radicals. It's very important. Okay. All right, any questions? All right, nice work. Let's go ahead and continue on. I think that's probably enough of solving equations with radicals. Let me just do number 13 real quick with you guys, and then I'll do number 14, and then we'll go on to the complex numbers. So here in number 13, I have the fourth root of u is equal to 2. So here, I want to get rid of the radical. But to get rid of the radical, notice all of these other problems were the square root, right? These were all the square root. And because it was a square root, that's why we squared it in order to get rid of the radical. But if you have a fourth root, you are not going to square it. You're going to raise it to, guess what power?
The 4th.
The fourth root, right? Because here, if you raise it to the 4th power, it's basically saying u to the 4th power and then take the 4th root of that. That itself will just become u. Because remember, when we're dealing with radicals, we're saying what multiplied by itself 4 times will give you the inside, right? So here, if I put u to the 4th power, what multiplied by itself 4 times will give you u to the 4th? The answer is just u. So that's why whenever you're wanting to get rid of a radical, you want to raise it to the power of the index. So the index is 4 here, so you want to raise it to the power 4, and that's why you get u. Same thing with what we did up here. The reason why we squared it is because this is a square root. So to get rid of a square root, you square it. To get rid of a fourth root, you fourth root it, or you take it to the 4th power. And then the right side, I need to raise this to what power?
The 4th.
The 4th power, great. So I also raise that to the 4th. Whatever you do once I do the other. So therefore, we get u is equal to?
64.
64 or 16? 16, I think.
Oh, 16.
Yeah, 16. Okay. So that's what you do with a higher root. You just raise it to the power of its root, and that'll get rid of it. Okay, great. Any questions on that? All right, so now let's look at number 14. So number 14 here, it's kind of a similar idea. X to the 1/4 is equal to 2. So there's 2 ways of looking at it. One way of looking at it is if I change this to a radical. If I change this to a radical, it's x to the 1, and the denominator is 4, right? So the denominator is going to be the 4th root. If you guys remember what we talked about the definition of a radical and its relationship with exponents. So here, if you remember the relationship between a radical and an exponent, what the first notes we took today, if you have something that's an exponent, you could change it to a radical. So a to the n, and then the denominator becomes the index of the radical. So that's what we did here. X to the first power, oops. X to the fourth power, x to the first power, and the index is 4. So that equals to 2, right? So this, I'm rewriting it as that. And just like what we did up here, how do you get rid of the fourth power? You raise this to the, or how do you get rid of a fourth root? You raise it to the fourth power. You raise both sides to the fourth power. And therefore, this just becomes x is equal to 16. So that's your answer for number 14. And I mentioned there's 2 ways of thinking about it. One is to change it to a radical, like what we did. And the other way of doing it is to just make the exponent 1. Make the exponent become a 1. So x to the 1/4, if I want to change x to the 1/4, and I just want to make this x to the first power, I can multiply this exponent here by 4. If I multiply the exponent by 4, 1/4 times 4 will just become 1, right? X to the 1/4 to the 4th power, that'll just become 1/4 times 4 is just 1, just x to the first power. And that's equal to 2, and since you raise this to the 4th power, you also need to raise 2 to the 4th power as well. And that becomes x to the 16. So either way would be correct. Either you change it to a radical form, or you just make the exponent become a 1, and you make the exponent become a 1 by multiplying 1/4 by 4. And since you're raising it to the 4th power here, you need to raise the right side to the 4th power as well. Any questions on that? I know I went through that a little bit quick, so just know that on your ALEX, you'll have plenty of opportunities to work on questions like these. All right, now last but not least are the last 5 problems. 1, 2, 3, 4, 5, actually 6 problems, and they are about complex numbers. So let me start a new paper on complex numbers.
That's what I have.
Yeah.
Complex numbers. So up until now, we have been dealing with what we call real numbers. So up until now, we have been dealing with real numbers. And when we say real numbers, we're saying that they are tangible numbers that you can measure, right? They're tangible. They're numbers like the number 4. 4 means that it's a positive 4, right? You could count 4. Or negative 4. Negative 4 means like you're moving backwards 4 steps. Or real numbers are also decimals, like 1.7, 2.8. They're things that you can measure. Real numbers are also fractions, right? Like 1/2, 3/4. We cook with those measuring numbers. So real numbers are things that are tangible and that you can touch. Complex numbers are another word for complex numbers are called imaginary numbers. So now in the complex system, so where it was before we were dealing with the real system, in the complex system, we have imaginary numbers. So that kind of seems really like mysterious and mystical, and it kind of is, right? Like, what are imaginary numbers? We think of imaginary numbers as like an imaginary friend or like something that's fake or not real, right? But basically, imaginary numbers are the opposite of real numbers. They're not tangible. You really can't measure them. So I'm going to put not tangible. And the reason why we have imaginary numbers is because there are lots of things in a physics and science world where you can't solve the problem using real numbers. So lots of things in science and physics and engineering and different things where you're going to get to some point in a problem, in a math problem, where you get stuck and you're like, I can't solve it. There's no real numbers that will give you the answer. And because of that, we use imaginary numbers instead to take its place. So you might be wondering, okay, so what kind of problems can you not solve using real numbers? Well, this is why it comes up in the section on radicals. So here, notes, if I had the square root of 4, what do you guys say the square root of 4 is?
2.
2, right? It's a real number, right? And the reason why it's 2 is because 2 times 2 will give me 4, right? Since 2 squared will give me 4. And that's why the answer is 2. But what if I give you the square root of -4? What's the square root of -4? Nothing, right? So before we would always say no real solution. And the reason why it's no real solution, since when we ask ourselves, what number squared will give us -4, right? We ask ourselves, can anything being squared give us a negative number, right? And the answer is there's nothing. There's no real number that when you square it, you'll get a negative number. So that doesn't make any sense. So that's why we say no real solution. But again, we don't just say no solution. It's not no solution, right? It's no real solution because there's no real numbers that will do that. However, this is where the complex numbers comes in. The square root of -4, I'll tell you right now, is going to be equal to, in the complex world, there is an answer, and then the answer is 2i. So there is a complex solution. There is a complex solution. So let's talk about what is the I, right? So definition. The definition for what I is, so I stands for imaginary. So I is equal to the square root of -1. That's the big kahuna definition for imaginary numbers. I is equal to the square root of -1. Because remember, in the real world, or in the real system, there is no such thing as square root of -1. There's nothing multiplied by itself twice that'll ever give you a negative number. But in the imaginary system, there is. It's going to be called I. And if I squared this, I squared. So remember, whenever you squared both sides when you square something with a radical, if I squared this, the radical disappears and you're left with the radicand. So if I squared this, what do I end up getting?
1.
Not 1, but
-1.
Right. Because remember, when you square something with a radical, all it does is that it removes the radical and gives you the radicand. And the radicand is -1. So this is also part of the definition as well. I squared root of -1 and I squared is -1. So that is why for this problem here, square root of -4, so what you do is you rewrite this as square root of 4 times square root of -1, right? You write it the real part and then the imaginary part, because 4 times -1 is -4, right? So square root of 4, we know that the square root of 4 is just 2. That's real. But then the square root of negative 1 is going to be I. So whenever you have a negative inside of a radical, you can consider that a square root of negative 1, which is just I. So this is really powerful because, and we're not going to get into this in algebra. Unfortunately, we're not, but when you get into higher mathematics, you'll find out that when engineers or physics or, you know, mathematicians or whatnot, when they are working on a word problem, like you end up with a radical of a negative number. When you work with real numbers, you're going to have to stop because you can't go any further. But because we have complex numbers, the complex system, we will have an answer. And that answer, when you keep moving forward with it, and later on in the problem, it'll help you solve the problem, and then it becomes real. Then you'll be able to have a tangible answer. One of the ways that I kind of think about this, and it's a little bit funky, monkey, I kind of think of imaginary numbers almost like the imaginary numbers or the complex numbers. I kind of think of it as faith. So for those of you guys that come from a faith background, whether it's Christianity, Catholicism, Buddhism, whatever, any type of faith that you might have, we say that faith is kind of like invisible, right? We think about God or angels or the spiritual realm. It's invisible to the human eye. However, what we see on the earth are the real things, right? So when we talk about real numbers, we're talking about tangible things. We're talking about things that we can touch, things that we can understand and measure and look at, right? We see trees, we see humans and all that stuff. But oftentimes in the real world, we can't solve all our problems, right? We can't solve all our problems in the real world. And that's where we turn to our faith, or we turn to imaginary things, quote unquote imaginary, meaning they're invisible. You can't really measure them, but you can't see them, but you know that they exist. So when we have problems in the real world that we cannot solve, that we realize, you know, this cannot be solved in a tangible way, we turn to things that are invisible, or we turn to things that we have faith in to solve some of those things. And then that in turn, those imaginary numbers that you use, or that faith that you use, in turn helps you to solve the tangible things. So that's what happens in science as well. When you're dealing with real problems that cannot be answered by real numbers, we jump into another realm, or a spiritual realm, or an imaginary realm, or a complex realm, whatever you want to call it. We jump into another realm to help us to solve that problem. And then that problem, in turn, it will become tangible, to have tangible applications. So with physics and engineering and all that stuff, that's kind of what it does. We go from the real to the imaginary, and the imaginary will help us solve the real. So it's kind of a cool thing in mathematics. That's kind of how I kind of think of imaginary numbers. It helps us to solve real problems when we're stuck with being unable to solve it with real numbers. So here, let's take a look at another problem. I have 10 minutes with you guys. So let's take a look at, that was number 15. Let's take a look at some of the properties. So the properties of imaginary numbers. So the properties, meaning like what rules do they follow, right? Like, do they follow, like, are they, like, what do you do with the I, right? We know I is equal to square root of -1, and we know that I squared is equal to -1. What can or can't you do with it? How do you add, subtract, and multiply and divide? So how do you add, subtract, multiply, and divide real imaginary numbers? And the good news is that it follows the same rules or the same properties as variables. So you kind of treat the I like it's a variable, and how you add, subtract, multiply, and divide variables are exactly the same way as you do with I. So that's a really nice and easy part. So let's look at number 17 here. Sorry if I'm moving too fast for you guys. Again, this will all be recorded, so you'll be able to look at the notes later as well. So the good news is that they work within the same rules as regular variables. So in question 17 here, I'm asked to add these two, and I notice that there's complex or imaginary numbers. So I just treat it like it's an X or Y or Z. So first I add the real part. So here's 4 and there's 3. I add it. 4 plus 3 is 7. And then there's imaginary part, negative 2i minus 6i. Well, I treat it like it's a variable. If it was a variable, what does that become?
Plus 6.
I'm sorry?
Plus 6.
Try again. What's negative 2i minus 6i?
Oh, 12i square.
Oh, so try again. So we're going to be adding. So make sure
Oh, okay.
we're adding here. So we're adding these two. What do they become?
Negative 8.
Negative 8. Negative 8 what?
I.
Great. And that's it. So complex numbers are actually pretty easy to deal with. So you just treat them like it's a variable, right? So if it's adding, then you just add them, right? And when it says in standard form, so when you write in standard form, it means that you write the real part first, and then you either do plus or minus, whatever, whether it's a plus or minus, here's a minus. So either plus or minus the imaginary part. So whenever you write down your answer, they say that the standard form is A plus or minus BI, meaning the real part plus or minus the imaginary part. So that's the form that you need to write it in. Always write the real part first and then the imaginary part. So here, let's make it a little bit more complicated. Let's look at number 18. So number 18 here, they're asking me to multiply. So again, we're going to treat it just like we do with real numbers. So I'm going to FOIL this, right? Or you could create the chart, whichever way you want. For the sake of time, I'm just going to FOIL it, just to go a little bit faster. 4 times 6 will give me 24. 4 times negative 2i. So again, I treat it just like a variable. I get negative 8i. Negative 5i times 6 gives me negative 30i. And then last but not least, negative 5i minus 2i will give me positive 10i squared. So that's what I got when I multiplied it all out. So now I'm going to look to see what combining like terms. I have 24 here. These are like terms. So I can add these two together. So when I add them together, I get negative 38i because they're like terms, and then plus 10i squared. So this is the only part that's different from variables. What is I squared? What is I squared equal to?
1.
Not 1, but
Negative 1?
Yeah, negative 1. So remember the I squared is negative 1. So this I squared here, I'm going to change that to a negative 1. So I actually have 10 multiplied by negative 1, right? So 10 times negative 1, 10 times negative 1 is negative 10. Okay, so whenever you see an I squared, you need to replace it with a negative 1. So 10 times negative 1 is a negative 10. So therefore, I have 24 minus 10 will give me 14 minus 38i. And notice that I write the real part first, and I write the imaginary part second, because that's what it means to write it in standard form. Does anyone have any questions on this? All right, I'm going to do number 19 as the last one. I skipped number 16 and 20, but if you guys need help on that, let me know and I'll create another video for you guys. But I covered most of this. For number 19 here, it says to divide. So what it means to divide is that we need to get rid of the I in the denominator. So just like radicals, it's very similar to what we did with radicals. We need to get rid of the denominator, or the radical in the denominator. We need to multiply by the conjugate. Do you guys remember that? So whenever there's two terms in the denominator, you need to multiply by the conjugate to get rid of radicals. The same idea when you have an I in the denominator, you want to get rid of the I in the denominator. So same idea as radicals, we multiply by the conjugate in the denominator. So to multiply this by the conjugate in the denominator, right now I have -4 plus 2i over -2 plus 5i. What's the conjugate of the denominator?
2 minus 5i.
Negative 2.
Right, it's going to be -2 minus 5i, right? So you keep the first number the same. It's only the middle that you change. So when you multiply by the conjugate in the denominator, what it's going to do is that it's going to get rid of the I in the denominator, just the same way as when we did radicals, it gets rid of the radicals. This is going to get rid of the I, and I'll show you how. So here, remember the shortcut? If you did this times this, if you multiply by conjugate, all you do is you square the first one, minus you square the last one, because the middle terms will cancel out, remember? So if you guys remember, A plus B times A minus B, you'll get A squared minus B squared, the difference of two squares. So here when I multiply the first terms together, so the first one, if you square it, -2 squared gives you +4, minus, and then you take the second term and you square it, well, 5i times 5i will give me 25i squared. And then, of course, the middle terms cancel out, so we don't even need to write them. So it's a squared minus b squared. So, but I squared, what is I squared?
-1.
-1. So if this is -1, so -25 times -1 will give me +25, right? So 25i squared now becomes -25i squared now becomes +25. So this denominator, therefore, becomes 29. Voila, no more i's, no more imaginaries in the denominator. The numerator, of course, is going to have a bunch of i's in it. I'll do this real quick just to save some time here. I get +8. I get +20i, -4i, and -10i squared. So I just FOILed it. I kind of did it in my head, though. I'm going to check my work. 8, +20, -4, -10. Right. So again, you guys can check it a little bit later. But once I get this, I'm going to combine like terms. This gives me -24i. This I squared becomes a -1.
Ain't that 16i?
I'm sorry?
Ain't that 16i? 20 minus 4.
10. Oh, yeah, you're right. Thank you. 16i. Thank you. +16i. Thank you for correcting me. When I rush, I make a lot of mistakes. This one becomes a -10 times a -1, so this becomes a +10. So 10 plus 8 here gives me 18 plus 16i, the top. And I'm sorry if I'm going a little bit fast, but this isn't the final answer yet, because remember, your final answer needs to be in the form of the real plus or minus the imaginary. So here, I have this fraction. I need to split up the fraction into the real, and the imaginary. So here, since it's a fraction, I'm going to split up the fraction into the real part. So 18 divided by 29 is the real part, plus the imaginary part is when I put the 29 over here. So again, I'm breaking up this fraction into the real and the imaginary part. So therefore, my final answer is 18 over 29 plus 16 over 29i. I'm sorry if I went through that a little bit fast, but again, this is all going to be all recorded, so I will put it on our Canvas Zooms or on our Canvas so you guys can go back and see it slower. Does anyone have any questions on this? Alrighty, so let me. All right. So start the video again. Okay. Hi. So without further ado, I want to make sure that I honor the end time. It's 3:30 right now. So thank you so much for joining. This homework, all 20 topics, is due on Thursday, midnight. Hopefully get it done by Wednesday. So when you see me on Wednesday, if you guys have any questions, last minute questions, you guys can ask me, because on Wednesday, we're going to start the new chapter. So the more you can finish by Wednesday, the better off you'll be. And if you guys have any last minute questions, feel free to just ask me and I can make a video for you or whatnot. I'll stay on for another 10 minutes. So if any of you guys have any questions, you guys can stay on. Otherwise, peace out. Good to see you guys. And I will see you guys on Wednesday.